bar I bar d t I w d t bar I bar w bar minus 3 mod of w squared. Do you agree? Are you with me, guys? Okay, good. Now, let's look at this term. So this guy we've seen is the derivative of w with respect to t, but we've just seen that w is not a function of t. So I remain just with w times k. So this will be w, which is w0 in our case, k ti. And similarly, this is just w0 bar k t bar I bar. So you see here, I get w times w bar. So I reobtain w mod of w squared, where here again, this is w0. So this part, I can write it down as k ti t bar I bar k ti k t bar I bar minus 3 times w0 squared. Now, this is something that you can check at home with calm. If you use these expressions for the scalar moduli and you plug them back here, it's a simple, it's an exercise you can do. Maybe not super simple, but it's an exercise. You can compute this thing, and for any Calabi-Yau, this contraction gives you 3 exactly. So this bit becomes 0. That's a very famous result that goes under the name of no scale. We will understand in a bit why it is called no scale cancellation. But that's good in a certain sense, because it tells you that the negative contribution here cancels off. So you're left over only with this potential. And you see, this potential is basically a modulus squared of dsw. This again a modulus squared of duw. So this potential now is semi-positive definite, right? Because it has only contributions which are greater or equal than 0. So it can be a complicated object, and now we want to find the minimum. But if this is greater or equal than 0, there will definitely be a minimum in the point where the potential is equal to 0, right? Because there will be a value, this will be a function of s and u. There will be some values of s and u for which the potential is 0. Now, when you move away from those values, the potential can just grow. So that means that that is a minimum. So there is a minimum, and in the minimum, the vacuum energy is 0, which is good because this is what we basically see in nature. So there is a Minkowski. So there is a Minkowski. Minkowski means that the vacuum energy is 0. Minkowski minimum at dsw equal du alpha w equal to 0, right? Because that's the point where if I set this to 0, if I set that to 0, I get the minimum. And these are the relations that stabilize. So these will fix S and U alpha in general for each alpha that goes from 1 to H12. So that's the way to get a Minkowski minimum. What happens to supersymmetry? So as I said earlier, the parameter that controls the breaking of supersymmetry is the F term component of each of these fields. And these F terms in supergravity look like this: e to the k divided by 2. Once you use the equation of motion, as I said earlier, k I j bar dj bar w bar. So if you compute now the F term of S, this will be e to the k divided by 2 k s s bar. Because of the factorized form, I have only this component. Now I have ds bar w bar. So what happens to this quantity now? When I compute it at the minimum, this is equal to 0, right? This is equal to 0 because of the fact that dsw, but this is the same as ds bar w bar, is equal to 0. So which means that the dilaton does not break supersymmetry. So that's supersymmetric, a supersymmetric solution. But the same is true for u, right? Because now I will have some u alpha, u bar beta dot, d u bar w bar. This is equal to 0. So this is supersymmetric. And basically I have a potential now, V, that, let's say that I denote collectively along this direction, u, alpha, and s. And now this is the direction of the t, I. So there will be one point here where there is a minimum, so where the potential along u and s here has got a minimum for a certain value where supersymmetry is preserved. But what happens in this orthogonal direction? So what happens to the t's? So once I sit, you see, at the minimum for u and s, this potential becomes equal to 0 exactly. So this means that the t's are flat directions. So they don't see any potential. So this potential is like a trough. So it's something like this, right? So, and this direction is flat. So this is still a modulus, or several, because they are flat moduli because there are several of them. Now, what happens to the F terms of these guys? I can compute also the F terms of the Ti. So this will be e to the k divided by 2 k Ti t bar j bar d j bar w bar. Now we've seen that this is just w bar k j bar. So this is e to the k divided by 2 w bar 0, the 3-level one. And then I have this k Ti t bar j bar k t j bar. So this is k t j bar t bar j bar. And again, you can do it as an exercise at home. A property of the Calabi-Yau is that this is minus 2 tau I in general for an arbitrary Calabi-Yau. So this goes, roughly speaking, is e to the k divided by 2 goes like 1 over the volume. So this goes like W0 bar with the minus tau I divided by the volume. Then there is also a factor with e to the k complex structure, e to the k with a dilaton, but I'm ignoring that. So now, what is the value of this F term? Is it 0 or different from 0? This is what we need to check now to see if supersymmetry is preserved or not. Well, it depends on the value of W0. So if W0 is 0, then this is 0. So it will be a supersymmetric Minkowski. But in general, W0, this depends on the fluxes. on the choice of fluxes here, but after you stabilize S and U, W0 is expected to be, and people check that in general, statistically, something over the 1. This is the flux landscape that also Professor Sen was mentioning yesterday. There are different possibilities for the flux quantum, and each of them gives you a different value W0. But statistically, most of the vacua will have W0 for the 1. So this is what you would expect. So now, can this be 0? Well, it can be 0, for example, if the tau I are 0. So that would be the limit where some 4 cycles shrink to 0 size. But this is not the limit where we trust the effectivity theory. So we don't want to be in the situation where the tau I are 0. The other possibility is that the volume goes to infinity. That will be a decompactification limit, right? Where the volume of the Calabi-Yau becomes infinite. So that will be the limit where you recover a 10-dimensional solution, because, right, you don't have any compactification anymore, which is a supersymmetric 10-dimensional Minkowski solution. But in general, you see that this goes back to the lack of predictability that I was mentioning yesterday. We don't know what is the value of T, of each of these Ti. So we don't know what is the value of the volume, because this is a flat direction. So it can be anywhere. So you expect in general that this is different from 0. So which means that you have a supersymmetry breaking Minkowski vacuum, which is perfect actually, because this is what we see in nature. But you don't know what is the scale at which supersymmetry is broken, because you don't know what is the value of this field. So you don't know exactly what is the value of the F term. And on top of that, you have massless modes, which is a problem, as we've seen yesterday, because of fifth forces, cosmological moduli problem, and so on. Okay, so that's the introduction. And by the way, here, supersymmetry is broken, and you have that the Goldstone fermion, so the Goldstino associated to the breaking of supersymmetry, is the modulino. So the I erased it here, but I wrote down, remember, the expansion of the chiral superfield. So this will be the modulino, so the fermion, which is the supersymmetric partner of the chiral here Killer modulus, which has the largest F term. Right? So the one with the largest F term will have the corresponding fermion, that is the Goldstino, that is eaten up by the gravitino, as we've seen yesterday, and the gravitino becomes massive in this situation. Now, why is this good for phenomenology? So at that point, we have these flat directions, and these are particularly good for cosmology. So now let's go to the talk. Let's see how much I can cover. If I don't finish, we go the afternoon. So now, forget about string theory. Think about your cosmology or general relativity course. And I hope you've seen this picture. Very good. So that's the standard slow roll picture, where one has to explain how inflation took place in your universe. And the simplest explanation is to consider a scalar field, which is slowly rolling down a flat potential. So when this guy is up here, this is a time-dependent solution, you see that effectively is mimicking a cosmological constant with a very high energy. So this will be the inflationary energy density. And you know that cosmological constant, a positive cosmological constant, gives you an accelerated expansion for the universe. Now, this guy rolls down up to a point with, by the way, with quantum fluctuations, which are responsible for the perturbations that we see, the fluctuations in the cosmic microwave background. up to a point where you see the mimicking of a constant, of a cosmological constant, doesn't work anymore. The potential becomes steep. This is phi end. So inflation ends at this point. So the universe stops its accelerated expansion. The guy goes down, starts oscillating around the minimum, and when it decays, it rehits the universe. So it produces standard model particles. So that's the picture. There are many models in the literature which can be confronted with data, for example, data from the Planck satellite of the European Space Agency. And so far, the best scenarios are the simplest ones, actually, in terms of a single scalar field, whose potential probably is not that simple, but looks like this. So very shallow potential. And the model that gives you the best fit to the data, so the amplitude of the density perturbations in the CMB, the spectral tilt, and all these properties, is something of this form. So it's a potential where there is a constant piece, and there is a piece that depends on phi. And when you go to large field values, this G of phi becomes very small, so that you are left over with just a constant. That's the model that gives you the best fit to the data. So now our idea is to use all this machinery, first in theory, to make contact with this picture. See, this is very excited and nice. And one of our fields here should play the role of the inflaton, phi. And very promising candidates are these guys. Because you see, these are leading order flat directions. So at 3 level, this is constant. So effectively what you expect that cosmologically, if you start from arbitrary initial conditions, the U and S field will reach the minimum. And then something has to happen along the direction of the T's, which is determined now by quantum corrections to the effective action. Because this treatment is just a 3 level, as we've seen. But there will be, for example, here, non-perturbative corrections, which depend on the T. And in the Kähler potential, there will be perturbative corrections, as well as non-perturbative corrections, which depend on the T fields, which will lift this flat direction. And the hope is that it becomes something like this. But you know that asymptotically, this becomes a flat direction as this one. That's very promising. Okay, so the idea is the following. We try to reproduce this loral picture using the type 2B Kähler moduli. There are different ways in string cosmology to do that. This is a class of scenarios that I will describe. Mahbub, for example, has been one of the founders of models where one was using instead brace and open string moduli. These are closed string moduli. It's a different possibility. What is this? Okay, thanks. Now, we remember that we want to get a constant. So let's see. The volume mode could be a possibility for phi to play the role of the inflaton phi. However, this does not work because of the fact that the volume mode couples to all sources of energy because of e to the k. Remember, there is, in the scalar potential, there is this e to the k, and k was equal to, at 3 level, remember k was minus 2 log of the volume, where the volume was a function of all my fields, the real part. But basically, the k is a linear combination of all these ones that corresponds to the volume. So you can consider a kind of basis in your field space where one combination of the t's is the volume, and the others are orthogonal to the volume. But the volume will always appear, right? You always have a dependence on the volume, so you cannot get a constant. Remember that we want to get something that effectively looks like this zero. Now, so cannot have a phi independent plateau if phi is the volume. So phi should be a direction in the space of the Kähler moduli, which is orthogonal to the volume. So for simplicity, let's consider a cabiao with with H11 equal to 2. So with H11 equal to 2, so you have two of these fields. I can consider one of them as being the volume, and the other is orthogonal to it, whatever that field is. I'm calling it tau phi, and that is a good now inflaton candidate. However, given that each term in the volume, in the scalar potential depends on the volume, to get a potential for phi, now phi is tau phi, this can be a constant only if I have some dynamics which fixes the volume, right? Otherwise, it is a function of the volume. It is not a constant. So, but not tau phi. So this means that I have these two flat directions, now the volume and tau phi. When I include quantum corrections, if I lift both of these directions at the same time, this picture will not work because V0 is not going to be a constant. However, if I have a dynamics now with a hierarchy, so if at leading order, let's say I just lift the volume, but tau phi remains flat, I can, when I look at the direction for tau phi, I can do it by fixing the volume. And now V0 indeed becomes a constant because it is just a function of the volume that reaches its minimum. So now it's a picture like this, for example, where, okay, consider that these U and S are integrated out. They are the third direction. They are fixed. So now let's say that I have the volume here, and here I have tau phi, that with this label phi means that this is going to be the inflaton, phi. If at leading order, I lift only the volume but not this guy, then if I have a contribution to the scalar potential, which is just a function of the volume, once the volume reaches its minimum, it becomes a constant. In this example, this constant is exactly 0, which will not work. So what we have to do, we have to consider a situation where once I stabilize the volume, I remain with some V0 that is different from 0, which is positive, right? Because I want to get, in the end, that this is this V0. Okay? And now this would be my flat direction, something like that. Okay? And so this would be the situation where you add quantum correction to the three-level action. Now I'm trying just to think about the picture. Of course, one has to check if this is true in the effective action. But if this is true, then there could be even further subleading corrections that lift this extra guy, but this will be inducing a tiny shift for the potential of the volume. And at that point, this will be slightly lifted, and you do generate this potential for tau phi. So that's the picture. So you have basically two hierarchies. So you fix first the compressed natural moduli in the dilaton at the high scale. Lower scale, you stabilize the volume, only the volume, with quantum corrections. So three-level first, quantum corrections, leaving tau phi flat. And then you have even more subdominant quantum corrections that lift the remaining tau phi, giving you a very nice potential that resembles what is needed to fit the data. This is basically what it means to say that tau phi is a leading order flat direction, which enjoys an approximate shift symmetry. it's approximate because it would be then broken by adding these subdominant quantum corrections. So that's the idea. And then you can go and check diffractive theory, and in certain regimes, this picture can hold. Basically, you consider the type 2B Kähler sector. As I said, at 3 level, there is a no-scale cancellation. Once you add 1 loop corrections to the Kähler potential, which in general depend on all the moduli, so they will depend on both the volume and tau phi, what happens is that they enjoy also an extended no-scale for an arbitrary Calabi-Yau, which is very good because it tells you that these directions keep remaining flat at leading order, even if you add 1 loop corrections. And then you can ask, what are the leading effects that break this no-scale in the plane volume and tau phi? And these are effects that indeed lift only the volume. So these are alpha prime corrections that appear toward alpha prime cubed. I mentioned them yesterday, computed by these people, and they are just a function of the volume. So they do exactly something like that. On top of that, there are different ways to get an uplifting mechanism, because what happens is that in general, these kind of corrections induce minima which are anti-de Sitter. So one has to add extra contributions to give a positive vacuum energy. And there are different ways. I've been working basically on all of them. And there are anti-branes, T-branes. These are basically non-zero F terms, if you are familiar with that, of hidden sector fields, which form backgrounds which are called T-branes. Or one can also look at solutions where the complex structure moduli, the F terms, here are not exactly or the complex structure moduli or S are not exactly equal to 0. There could be one could find solutions where these are different from 0. So then the potential at leading order is not exactly 0. It's a bit positive, and this can counterbalance some negative contributions and give you the Sitter solution. And then there are also other effects that this is too technical. Maybe I can skip it. But the point is that this picture in general seems to hold. Of course, it's complicated to compute all these alpha prime and loop corrections, but we try to do what we can. And at the moment, it seems that, at the moment, I mean, with our current knowledge, it seems that this works. So the idea is, to repeat myself, is the following. So there's this potential with volume and phi, now this is tau phi. There's a total potential with 1 leading order flat direction. So there will be this leading order, leading, considering the corrections beyond 3 level, that lifts the volume, and a subleading correction that lifts tau phi, but is also a function of the volume. And you can find the minimum, and this minimum gives you the value of the volume and tau phi. But basically, the total potential in the end should have a Minkowski vacuum. So this basically is telling you that this V0 here is positive. Then when you lift this flat direction, in general, what happens is that this gives you a negative contribution that is counterbalanced by V0 to get basically a Minkowski minimum. This is what happens. So that the total potential at the minimum is 0. But now, this basically that picture, when you ignore the lifting of phi, you have this positive V0 that is left over, where this positive V0, if in the end I want to get a Minkowski vacuum, has to be of the same order as the value at the minimum of the subleading potential. That is going to be negative, but it's counterbalanced by this V lead positive, and then I get that. What about the subleading dynamics? Now you can set the volume to its minimum, as I said earlier. So the volume is heavier, and in the early universe goes to the minimum. Then I look at the orthogonal direction. So I can set V equals to its vacuum expectation value. Then the potential is going to be a function just of tau phi, and is going to get exactly this form, the form that I mentioned at the beginning, where V0 is the value of V sub, where both of them are in the minimum. So it is this, V0. And this G of phi is basically given by the subleading potential as a function of tau phi divided by the potential at the minimum. So now this tau phi, which tells you exactly what is the shape of this potential, depends on canonical normalization, because as I said earlier, these fields are not canonically normalized. So remember that the kinetic terms were given by the second derivative of k with respect to t bar, d mu t bar. So these are not canonically normalized. So now this is tau phi. So I will get the second derivative of k with respect to some tau phi squared d mu tau phi, d mu tau phi. So here in general is more complicated, but the scaling is this one. So you see that in general, this is a function of tau phi and the volume. So one has to redefine the fields to go down to something that looks like 1/2 d mu phi, right? To get the canonical kinetic terms. And then given that tau phi is a leading order flat direction, you know that when you go to very large field values, the potential should approach V0. So you need to have something like that. Now, to go down to data, so to be able to match observations, one has to know what is exactly this function g of phi. So you know that it's going to be approaching a constant, but of course the tilt is very important now to match the data. And this is going to depend on two features. That's important. One, of course, is the origin of the potential which lifts this flat direction. So depending on which correction you use to lift this flat direction, you get something different. And qualitatively, you can have perturbative effects or non-perturbative effects. Now, when you do it with perturbative effects are power-like. So they go like 1/tau phi to some power p, where this p is positive, and that tells you that these are suppressed. This correction, they are subleading because of this suppression. So they go to 0 when tau phi becomes big. The other possibility is to have non-perturbative effects. In general, they go like e to the minus k tau phi. For example, we've seen yesterday that G Yang-Mills to the -2. So this was the coupling of an SUN theory, living on the 7 branes, wrapping a 4 cycle. Remember, this was going like tau. So if I have something that goes like e to the minus tau, this is e to the minus 1/G Yang-Mills squared. So this is the typical behavior of non-perturbative effects. So you see that they behave like this. And again, they are small because they are non-perturbatively suppressed. With k positive, they would go to 0 when tau phi goes to infinity. So this is approaching the constant. On top of that, I need to write down the potential in terms of phi, so I need to do the canonical normalization to write it down as an explicit potential. And now this canonical normalization in general depends on two possibilities. So basically, if tau phi is a bulk modulus, so bulk means that it controls the size of the extra dimensions. And that's the possibility when you have some kind of vibration. So the simple situation where H11 is equal to 2 and the Calabi-Yau looks like a base times a fiber. So there are two moduli, and then you have the overall volume and let's say the fiber, which could be tau phi. And in this case, you have a canonical normalization which relates tau phi to the canonically normalized inflaton, which is exponential. Is e to the lambda phi, where lambda is a number that one can compute exactly, but it is of order 1. The other possibility is that the inflaton is not a force cycle controlling the overall volume, but is a local blow-up modulus. So it is something that, let's say you have your Calabi-Yau, so it is not something that controls the overall volume, but there is some singularity somewhere and which can be blown up. So locally you do a blow up of a singularity, so making it smooth. And that would be the situation of a local modulus in the sense that it is localized around the singularity. So in that case, there is a different relation between tau phi and phi, which is power law. It's not exponential anymore. So tau phi goes like the volume to the 2/3, the constant, and then phi to the 4/3. Now, basically, this is the picture that became clear to us after doing a lot of model building, because this looks now as a very nice top-down understanding, but this is not how we developed that. The way we did that was to check cases and then, oh, it works. No, it doesn't work. No, it works. And in the end, we just look at that and we systematize, let's say in this way, the understanding. And basically, you can combine now 1 and 2, and you get 4 possibilities. So you can have that you lift the flat direction with perturbative effects, and this can be either a bulk or a local modulus. Use non-perturbative effects, and it is a bulk or a local modulus. And then you get different models that people work out in the literature, which are these ones. So these are all models that reproduce this potential, which is a constant minus g of phi that becomes small when phi is big. So the first possibility, actually this was historically the first derivation of an inflationary model using the Kähler moduli. And so in this case, the inflaton is a local modulus, it's a blow up, and you use non-perturbative effects. And then you see g of phi, when you use non-perturbative effects, is exponential in terms of phi. You do the canonical normalization, which is power law, and you get e to the minus something that goes like phi to the 4/3, which indeed is very small when you go to large phi. The second possibility is to use not a blow-up modulus, but a fiber modulus, so a bulk modulus, with non-perturbative effects. And now the difference is that non-perturbative effects give you e to the minus tau. But then, as we've seen, tau in this case is related to phi with an exponential. So you get a super flat e to the minus e to the phi potential. And then there are other models where people instead use loops, so perturbative corrections, which now are power law. They go like 1 over tau. Then if you do it with a bulk modulus, this is an exponential. So you get e to the minus phi, again, a negative exponential. With the difference, by the way, between these and that case, because in the end they look similar, the difference is that this one has got a coefficient, which is the volume to the 2/3. And as I told you, to trust the effective field theory, the volume has to be big. So this is flatter than that, because here these p and lambda are all order 1, k and mu are of order 1, but this has got a larger coefficient. And the last possibility that we discovered very recently that we missed in the past. The reason why we missed it in the past, we thought about that, but we thought that it would never be possible to get it with an effective field theory that is under control. But recently we realized that this was not true. And it is to use loops with a blow up. In that case, loops are power law. The canonical normalization is power law again. And you get, for the first time, a potential that is not exponential. And it goes like 1 over phi to some power. And again, we found that this power here is 1/2, so that you get 2/3. And that's the potential. So that's the picture. And let me tell you how this model works. I'm focusing now on the last case. So we take a Calabi-Yau now that looks like this. So going back to this picture, there is some big cycle, so tau big, that controls the Calabi-Yau. And you see there are minus signs here. So basically tau S stays for small. Tau phi is going to be the inflaton. That's why I put the label phi. These are like holes here in the Calabi-Yau. So this will be tau small. This is tau phi. That's why sometimes these are called Swiss cheese scenarios, right? This looks like a Swiss cheese with holes. And these are blow-up modes of local singularities. So then you see that in the limit where the big cycle is much bigger than the others, this can be approximated as tau big to the 3/2. And remember that these are all the real parts of Kähler moduli, which are complex. So each of them comes along with an axion. And now let's see at what the quantum corrections do. So remember, at 3 level, we had k minus 2 log of the volume. Now I'm ignoring the dilaton and the compensation moduli. I'm considering them fixed, but they will be there. W was just W0. Now is a constant after I stabilize S and U by background fluxes, and it's expected to be of order 1. And then I add corrections. So these corrections are the corrections of order alpha prime cubed that I mentioned earlier. So these are corrections that in 10 dimensions arise at order alpha prime cubed. Then you can dimensionally reduce, go from 10 dimensions to 4 dimensions. And you see that they depend on a quantity that in turn depends on the Euler number of the Calabi-Yau, just a topological quantity property of the Calabi-Yau. And then you have these 3 to 3/2. And then you can add also non-perturbative corrections that depend on tau S and tau phi. You can think about them again as having a stack of these 7 branes wrapping this cycle and the stack of these 7 branes wrapping that cycle, as we've seen yesterday. And there could be non-perturbative effects in these field theories which generate these corrections. Where now capital A and S and capital A phi are constants, and the same for these little AS and little A phi. These are also constant at this point, psi, and GS, by the way, is supposed to be small. Supposed to be small via destabilization. So via the freedom that you have in choosing fluxes, there will be some solutions where the fluxes induce a potential such that the minimum for S gives you a small G string, so that you can trust the fact that loops are small. Okay, you use this expression for K and W and you plug them into here. Use general expression for the F-term scalar potential. Again, it's a long exercise, but you can see that in the end, you get indeed the leading order potential and the subleading potential. Now, this leading order potential depends on the volume and tau S. you see there is no dependence on the dilaton tau phi. Only the subleading potential depends on tau phi. Now let's look at the leading potential. So you see there is a contribution from the alpha prime. Well, first of all, see that if you set this correction to 0, so psi is 0. If you set this to 0, the capital I's, they become 0. This will become 0. So the capital I's enter here because you see these are the non-perturbative corrections. They will become 0. And basically, you recover the leading order no scale cancellation. So then this is generated by alpha prime corrections. These are the non-perturbative corrections which depend on AS, TS. And then we added also an uplifting contribution which can have different sources. If you want, we can discuss during the breaks how to get that. But that is just a function of the volume. Now, these corrections, if A phi is much bigger than AS, then they will be more exponentially suppressed, and they generate a subleading potential that you see now depends on tau phi from this and the volume. So leading order, you can now search for minima of this potential, which is just a function of the volume and tau s. And you can see that there is a Minkowski minimum, indeed here, when the three terms balance each other. And that's the solution to the dying cyber problem that I was mentioning last time. Because here we are not finding a minimum by balancing different terms in the same expansion, but we are balancing different terms in different expansions. Because you see, we are balancing alpha prime corrections. So this will be the leading order of alpha prime correction. Subleading alpha prime corrections, if the volume is big, are supposed to be negligible. And we are combining them with non-perturbative effects, which are also the first order in a non-perturbative expansion. How can we do that, given that these are exponentially suppressed? Well, you can do that because of the fact that these cycles S and phi are much smaller than tau big. So basically, here you get some e to the minus tau s, but if the volume is exponentially large, then you see that effectively this term, given that size of order 1, the string doesn't give you a very big factor. This goes like 1 over volume cubed. Okay. Now this guy goes like 1 over the volume, and then if the volume is the exponential of AS tau s, this will give you also 1 over volume squared. So this will also go like 1 over volume cubed. This term here as well will go like 1 over volume cubed, naturally. So this is where the minimum of the system will be. So this is where the minimum will lie. And then you can check what is the minimum for tau s. This goes like 1 over G string. So indeed, you are in a situation where fluxes stabilize the dilaton that gives you G string, let's say of order 0.1 or whatever is enough to trust perturbation theory. Tau s, now let's say if GS is 0.1, tau s is of order 10. If psi is of order 1, which is good. So it is still in a regime where you are above the string scale, so you can trust the effective theory. And then the volume is huge. The volume is exponential of tau s and tau phi. And then you have this subleading potential. Now, what about loop corrections? So I'll try to be simple here, because I didn't include loop corrections. So if you go back, I included here only alpha prime corrections, but there will be some G-string corrections as well. And I have to be careful because it could be that these G-string corrections ruin this hierarchy. And by the way, this is the hierarchy that was used in this model. So the first model that was developed in the literature, this non-perturbative blow-up inflation, was basically this scenario, where now this potential is the potential for the inflaton, right? Because a leading order, you stabilize the volume and tau s. A subleading order, the volume is fixed. You have only a potential for tau phi that is exponentially suppressed. When you go to very large tau phi, this potential goes to zero and you remain with a constant from the first piece. So that was the idea, the original idea of the people there, Colin Quevedo and Kaufman et al. However, one should be careful because you can start thinking about what happens when I go to very large tau phi. So when I go to very large tau phi, so moving this away from the minimum, immediately these two guys become exponentially suppressed. So they become super small. But who tells you that there is no loop correction here that is power law that becomes bigger than this? So it could be that basically you think that you get a flat direction just considering non-perturbative effects. So you go at large tau phi, the non-perturbative effects go to zero, but it could be that loops are important and they destroy the flatness. So that's why we started investigating the behavior of these loops. And that's a very complicated topic. These have been computed, at least I want to give you an idea, exactly only in toroidal orientifolds. So simple examples when you have tori, so not when you have a Calabi-Yau. The worldsheet computation is not doable for a Calabi-Yau. And that's the situation basically where the volume looks like that. It's the square root of tau 1, tau 2, and tau 3. That's the situation where you have tori. And these German people found that there are two kinds of corrections that they named Kaluza-Klein and winding. So these are loop corrections. And this is the result for the toroidal case. They found that these are open string one loops, so loops of open strings. And you see the first situation is basically something like pictorially when you have brains. In this case, it could be 2d7 brains. Then there are open strings, and there is a loop of these ones. So there is an open string one loop that you can interpret also as, you see, a three-level exchange of a closed string. And these strings carry Kaluza-Klein momentum. And basically, this is the Kaluza-Klein scale associated to, if these are the 7 brains, so they wrap a 4 cycle. So here, the transverse direction would be a 2 cycle. So that's the Kaluza-Klein scale associated to this transverse 2 cycle between parallel D7 and D7. And they found this behavior. So G string, then some coefficients which depend on the complex structure moduli that for us are constants because they've been stabilized. And then they have 1 over tau 1, 1 over tau 2, 1 over tau 3. And if you compare them with these, okay, well, this can be a bit worrisome because you see that this potential basically, when you expand it, let's say it's k is minus 2 log of the volume plus something that goes like psi over 2 G string to the 3/2. Then you can expand it for large volume, so it would become minus 2 log of the volume. And you can factor out the volume, and then you get something that goes like minus psi over G string to the 3/2 divided by the volume, something that goes like that. So then you see that this correction goes like 1 over the volume. And sorry, what is it here? Whereas these loop corrections, these at least in the case of tori, they are corrections that you should add here, plus delta k g string. And if they go like 1 over tau, you see this, if this goes like 1 over tau, whatever tau that is, if this tau is tau big, so, or I call it tau big, we've seen here that the volume goes like tau big to the 3/2. So then this correction would go like 1 over volume to the 2/3, right? So this would tell you that ignoring this correction is wrong, right? Because this correction is not more suppressed than that. If you are at large volume, here is volume to 1 power, here to 2/3, this is actually bigger. So one should have included these corrections. So that's something that one should be worried about. And then there is a second kind of corrections. These are instead originating from the 3-level exchange of winding closed strings, the D7 intersection. So that's a situation where you don't have parallel D7 branes, but they intersect. Okay, they intersect over a 2-cycle. Both of them wrap a 4-cycle, so they intersect over a 2-cycle. So now this is a 2-cycle, and then you can have closed strings which wound around a 1-cycle actually inside this 2-cycle. Is what happens, and now you generate these corrections that go instead like 1 over tau, 2 tau 3, tau 1 tau 3, but they go like 1 over tau squared. So these extra corrections would go like, so these extra corrections would go like, so this will be the Kaluza-Klein correction. Then you have the winding correction. This would go like, might go like, let's say, 1 over tau big squared. This is good. It would go like 1 over volume to the 4/3. So this will be smaller than that. So it's less worrisome. But one should take care of that. However, these corrections are there for toroidal orientifolds, not for Calabi-Yau's. And people tried to conjecture the form. You see, 2 are the same authors of that paper, of this one loop correction to the Kera potential for an arbitrary Calabi-Yau. And the way they did it was basically by rewriting down these expressions in the following way. And if you do it basically by using the expression of the volume, now these corrections can be written down as the sum with some coefficient of Ti over the volume. You have 1 over the volume. These are the sums of these Kaluza-Klein scales to the -2, which somehow makes sense because this is the 3-level exchange of a string carrying a Kaluza-Klein momentum. So it's the propagator 1 over the mass squared. And then you have the 1 over the volume that is always there to go from the string frame to the Einstein frame. So if you rewrite down these corrections in this way, it looks, I mean, the physical meaning looks clearer. And then you can conjecture that also for a Calabi-Yau, you should have this feature. So then when you have Calabi-Yaus, you have parallel branes. You look at a 2-cycle that is orthogonal, you associate this a Kaluza-Klein scale, and you use that formula. You can do something similar for the winding corrections, and it becomes now 1 over the volume and 1 over m winding squared. However, if this is true, something that we discovered is that in full generality for an arbitrary Calabi-Yau, there is this extended no-scale cancellation. Which means what? Which means that this correction, even if, this correction that is generalized to that expression, even if it is dominant over the alpha prime corrections at the level of the scalar potential. Once you go to the scalar potential, this is the quantity that you should care about, these loops cancel off. So there is still a higher order cancellation. So basically, once you have this relation and you add here this delta k, you keep getting 0. That is why it is called extending of scale. 0 at leading order, and but then you get something non-zero from these corrections. So these do not experience any no-scale cancellation. However, they would be subdominant with respect to this guy. So I think this is very nice because it tells you that the stabilization mechanism that I presented before is robust under these loop corrections. However, they can still ruin the flatness of the inflaton potential. So going back, this means that if I now add loop corrections here, following this Calabi-Yau conjecture, they will not destroy this leading order stabilization. They will appear as sub-leading order, but they could still be bigger than these non-perturbative corrections when you go in the regime at large tau phi. So they're smaller than the alpha prime cubed correction. So the minimum where the volume is exponentially large is still valid, but they might ruin this flatness. And we will see that, I think, now in the afternoon, because it's time to stop. Maybe we will restart with something that also we try to give. It's a low energy interpretation of the behavior of these loops to strengthen this Calabi-Yau conjecture. But we will see it in the afternoon.